Guys, this is Gantulga bat bulb, and my partner is David White, and we made a control card that drives it by itself and avoids magnets. So the main purpose of this car is to avoid magnets. And how does it do that? So basically, this is the flow chart of our circuit. You have switches, which is magnet sensors on the car that senses magnets. So when it senses a magnet in a certain range, the switch closes. So depending on how the switches act, the input goes through a summing amplifier, which inverts the input. And we need a summing amplifier so we can use multiple switches, and the car will take account in all those switches when making a decision. And that input goes into the comparator, and depending on the polarity of the output, the motor either goes forward or backwards. And same for the turning motor. Depending on the output of the comparator, it's either going to turn right or left. So if you look at the pictures, these white things are the magnet sensors, so they close and open when they sense a magnet nearby. So this is the PSpice, our PSpice simulation. As you can see here, at first these are the switches. So before the switches are closed, there's only one input over here. Only one input, so the car is always going forward. But if the switch is closed, now you have inputs coming here, and all of those inputs are in effect. So what you end up having is having two inputs to the comparator, which is right here. And since the feedback resistance resistor is higher on this summing amplifier, it ends up creating a difference in the inputs, which changes the output of the polarity of the output. So that's how the car changes directions. And everything on the left side is for the forward and backwards motor, and everything on the left side is for the left and the right. So the difference between them is, for the motor that turns left and right, there is no input that's constant at the beginning, because we don't want the car to start by turning. We want it to go straight. So let's look at the car one more time. If you see right here on the top right corner, we have a op amp that has the red wires. So those are the comparators, which leads up to the motors. And down here we have the two summing amplifiers. And this one has the higher feedback resistance in case the switch closes, so we can have the difference on the comparator. And that's basically, so this is the back two sensors, switches, or magnets, whatever you want to call it. So we have we had several source powers, because we have to power each op amp separately. And so we had two 9 volts batteries, which you can see we had to power with these, and we also had another battery on the bottom. That's about. And one more thing to note, when we were testing it on the breadboard, it worked fine, but when we hooked it up, it wasn't running. Hooked it up to the motor, it wasn't running correctly, because the motor wasn't getting enough amperage. So we try to fix that problem by building a H-bridge. So basically, what an H-bridge is H-bridge is commonly used configuration for designing motors that will both go forwards and reverse. It is made out of transistors that act as electronic switch that will either open or close depending on the current moving from the emitter to the base. but unfortunately, even after that, the motor wasn't getting enough current, so we just tried it with just 2 PNP transistors and 2 op amps, then reversed the polarity of one of the batteries. So I have a video of it working on the breadboard. So as you can see, we're simulating the switches using the breadboard, but you can see the wheels switch directions when the switch turns on and off. And that's about it. Thank you.